Don't write it. Don't write it. It's clear that from there. It's clear from there. So, please come back. Yeah, that's one can find the matrix from there. I will try to first of all comment and tell you why your form is a priori, without looking at the matrix, does not satisfy what we want. So let me explain. Instead of I call it 1, 2, 3. Okay? So you have transfer of 1, 2 to 2, 3. So your matrix will be of the form T of the pair sigma 1, sigma 2, transfer to the pair sigma 2, sigma 3. Two pairs. Okay, this is your matrix. I will take now the next matrix. The next matrix will be T, sigma 2, sigma 3, transfer to sigma 3, sigma 4. Right? That's the next one. Then you want to say, when I sum over the four values of this, do I get a matrix product? So, question, what is sum on sigma 2, sigma 3 of this? I don't know. I don't know, because when I sum on sigma 2, this changes. It's not fixed. This is not equal to matrix T square of sigma 1, sigma 2, comma, let me put a bar, sigma 3, sigma 4. Because you have summed on sigma 2. So I don't know how to make a matrix product. Do you see what I mean? When I take these two and I sum on sigma 2, sigma 3, this is not a matrix product because the line there, the row varies. The matrix product should be of the form T, A, B, T, B, C, sum on B. And A and C are fixed. That's a matrix product. Here, when you sum on sigma 2, sigma 3, A is not fixed. But still, whatever you get, you cannot take the power of this matrix because of this structure. Such a structure is not a matrix product. Whatever you write here, it cannot give a matrix product. A matrix product is A fixed, C fixed, sum on B. So here, sigma 2, if you have to, matrix product should have sigma 1, sigma 2 fixed, sigma 3, sigma 4 fixed. But you are summing on sigma 2, sigma 3. So that doesn't work. No matter what is the matrix. It's not a matrix product. Now, this one is nearly the same, except that it's 1, 2, transfer to 3, 4. That's the idea. The group 1, 2, transfer to 3, 4, then 3, 4 to 5, 6, etc. That's the idea. Okay, that's this matrix. Take 1, 2, transfer to 3, 4, and then 3, 4 to 5, 6, 5, 6, etc. Transfer of pairs. That will get a matrix structure. So this is right, nearly right. Nearly right. So there's still one slight mistake. So what is it? It looks right. It looks right because you have written here the interaction between 1 and 2, the interaction between 3 and 4, I'm sorry, between 2 and 3, and the interaction between 3 and 4 is missing. 3, 4 is missing. Okay? This term was missing. You agree?
But we don't need this term. It's in the next.
Ah, you have chosen that. It will be in the next one. Okay, you're right then. Another way is to take my way, but you put here 1/2 and here 1/2. That's the same. That's the same. Okay, you're right. I apologize. You're right, provided you put a 1. So you have two choices, like yesterday.
Yes.
This choice is correct. So you win. Okay? I'll offer you a drink. Or whoever found it. Good? So this is a metric structure. Do you understand? The structure will have T, sigma 1, sigma 2, sigma 3, sigma 4. The next one will be T, sigma 3, sigma 4, transfer to sigma 5, sigma 6. So when you sum over sigma 3, sigma 4, those guys do not change. So this is a matrix product. So that's the difference. You see, here, this doesn't give a matrix product. I have not convinced you? No. We'll discuss it in private. But you have to be sure, like here, that if you want a matrix product, that these external indices do not change. Otherwise, you don't get a matrix product. Okay? We'll discuss it later. Okay. So, what happened yesterday? We solved the one-dimensional case exactly, and we found that the result was not interesting because there was no phase transition. You could say, well, if I take another model, like one of those that we have discussed, maybe this other model may have a phase transition. So we want to understand why no model in one dimension can have a phase transition. So, before I do that, I will return to the Ising model, and I will make another calculation. I take the Ising model, 1D, zero field. So, E minus J and as you remember, there are several ways of looking at phase transition. One way was to look to see whether there is long-range order. So I will calculate the correlation function between the spin at site A and another at site B with the distance B minus A. I will look at what happens when B minus A goes to infinity. So what is sigma A, sigma B? This is 1 over Z, sum over configuration, exponential minus beta E, C, times sigma A, sigma B. That's the definition of the expectation value. So let's take our chain. I will put it in a circle because it's slightly simpler, but doesn't change anything. 1, 2, here's someone there. There is A, there is B, and here there is N. That's my chain couple. This is A, and this is B. So let's start again, as we did yesterday. I will start by writing the factor T, as yesterday, sigma 1, sigma 2, T sigma 2 sigma 3, T sigma A minus 1 sigma A, then I will write the sigma A, then I will write T sigma A plus 1, then I will write T sigma B minus 1 sigma B, then I write sigma B, then T sigma B plus 1, and I will end up with T sigma 1 sigma n sigma 1, and this is equal to this, sum over sigmas, 1 over z. Same story as yesterday. T is the same T for the Ising model. So a lot of things are simple. Sum on sigma 2 is simple. Sum of sigma 3 is simple, because it's still our metric structure. So this is 1 over z, sum. So first, I sum here on sigma 2, sigma 3, everything up to sigma A. So how many terms do I have? A minus 1. I go from 1 to A minus 1. So I get the power A minus 1 of the matrix T, matrix element, sigma A, sigma 1, sigma A. Then I get sigma A, and then again I sum here. I can sum all intermediate indices. So I have a power, the matrix T, which is the number of elements which go from A to B here. So how much is it? It's B minus A or B minus A minus 1. I have to look at it. To be careful, matrix element, sigma A, sigma B. And then I go from B to N. So I have T to the power N minus B. If B was 1, I would have N, so it's N minus B plus 1. Sigma 1, sigma B, sigma 1. And my only point is here, is it, I should have a total of N. Yes, this is right. So everybody sees that? It's the same story as yesterday. The sum which remains are sigma 1, sigma A, sigma B. You see that? I have sum of everything which was simple in between. So I will introduce a matrix, tau, which is equal to 1 minus 1. This matrix is sigma A. Sigma A equal plus 1, this is element. Sigma A is equal minus 1, this is element. So I have my correlation function. I can write it, T to the power A minus 1, sigma 1, sigma A, tau A, you see. Alright, let me write it like that. I will try to be a little quicker. State tau, T to the B minus A, I've forgotten sigma B here. I'm sorry. I've forgotten sigma B in between. Forgot this guy. Forgot this one. So here again tau, and here I have T to the N minus B plus 1, and the whole thing is matrix element sigma 1, sigma 1. sum on sigma 1. So let me repeat. Why is it simple? If I introduce this matrix tau, this is again a matrix product. Because if I take, I hope you see that. T tau sigma 1 sigma 2 is T sigma 1 sigma 3 tau sigma 3 sigma 2 sum of sigma 3. But tau is diagonal, so tau of sigma 3 sigma 2 is a delta function of sigma 2 sigma 3. But it's equal, this delta function is either, so this contains sigma 3 should be equal to sigma 2, and the result is, so let me write in words, this is just T sigma 1 sigma 2 times sigma 2, because tau, when it's diagonal, is sigma 2. So this is what I have used here. Whenever I solve sigma A, I say, well, this is a product by matrix tau. Then I have T, then again product by matrix tau, and then I have T again. So this is how I reach this. And this is nothing but the trace of T to the A minus 1, tau, T to the B minus 1, A, tau, T to the N minus B plus 1. And because the trace is commutative, I end up, I can cyclically invariant. I end up with a simple formula. Sigma A, sigma B. Equal trace of tau, Tb minus A, tau, T n plus A minus B. Because I'm cyclically invariant, I can put this, come here, and I have this. Okay, looks strange. Let me look at my notes somewhere. Looks strange. That's right. Okay. So now what do we know? 1 over z. I'm sorry. Forgot 1 over z. So z is lambda 1 n plus lambda 2 to the n. Lambda are the eigenvalue of t. So there are two eigenvectors, which I will call 1 and 2. And the matrix T in zero field is really trivial. It's exponential beta j, exponential minus beta j, exponential minus beta j, exponential plus beta j. So the eigenvector 1 is the vector 1, 1. You see that if I take the vector 1, 1, this is an eigenvector. And I normalize it by square root of 2. And lambda 1 is exponential beta j plus exponential minus beta j, 2 cosh beta j. The vector 2 vector 2 is 1 minus 1, because if I put minus 1, I get exponential beta j plus minus beta j, and the other one is minus sign. And lambda 2 is 2 sinh. So indeed, cosh is larger than sinh, as you know. Now, the matrix T so the matrix T, I can write it as lambda 1 times the projector on vector 1 plus lambda 2 times the projector on 2. That's the matrix T. This is the projector on vector 1. This is the projector on vector 2. T to power n has the same eigenvector, but powers here. Okay, so I will put that into the top formula, and I will get lots of terms. But one thing which will simplify is that 1 tau 2 is 0. Indeed, let me do the exercise. If I act on 2, I get the vector 1, 1. So this is 1, I'm sorry. If I properly normalize. However, 1 tau 1 will be 0, because 1 tau 1 is equal to this, which is orthogonal to 1. Same is true for 2 tau 2. Good. So with that, we can do the calculation. So I take the first. This is t to the b minus lambda 1 to the b minus a 1 1 tau. I have also 2 2. I'm sorry. I replace each t by this formula. So let me do it. I first take for the first t lambda 1. For the second t, I should take lambda 2, because otherwise I have written this part here, which goes from b minus a. I've written this. When I choose for t this first term, so I keep with this first term. For the second one, since 1 tau 1 would be 0, I have to take 2. Then I have to take here tau and the trace. But I had another choice. In which I took 2 here. Then, because I have a tau, I should take 1 here. And then 1. So this is this sum. Okay? 1, 2, 2, this is 1. This factor is 1. Then cyclic invariance of the trace. I can put here my tau and here 2. So I get, for this correlation function, 1 over z, lambda 1, b minus a, 1, 2, lambda 2, n plus a minus b, and then here I have 2, tau, cyclic invariance of the trace. I would put here my 1. And the same for the other term. I'm using the trace. So you see, the first one is just tau 1, 2 again. This is a number. So I get equal 1 over z lambda 2 to the n plus a minus b times lambda 1 to the b minus a plus lambda 1 to the n plus a minus b times lambda 2 to the b minus a. That's the end of the calculation. No? I've lost you? Okay, let me repeat because it's not difficult. I look at there were lots of terms because any t here is a sum of 2 terms. So a priori there would be 4 terms here. 2 of them vanish because of that. So we are left with 2 terms. These 2 terms involve tau with 1, 1 and tau here with tau 2, 2. But I can put, you see that because of cyclic invariance of the trace, I can put my 2. Okay. All I'm saying is that the trace of tau 1, 2 is equal to the matrix element tau t1, which is 1. This is all I'm writing. Okay? Because if I want to calculate the trace, I have to I calculate it by taking the value with the vector 1, 1, which will be 0, and 2, 2, this is 1, it's tau. So that's it. So this is the first term, and the same for next term. So we get this result, this correlation function. Now, n is large. Lambda 1 is greater than lambda 2. Cosh is always, this is cosh, 2 cosh beta j, always greater than 2 sinh beta j. So if I take the larger limit, the leading term here for n large is this one. I will factor lambda 1 to the n, both in numerator and denominator. And here I will get lambda 2 over lambda 1 to the n plus a minus b. And here I will get lambda 1 over lambda 2, lambda 2 over lambda 1 to the b minus a. I assume that b is larger than a. I want to let b minus a go to infinity. So this is the same. I've just divided. N goes to infinity. Lambda 2 smaller than lambda 1. This is very small. This is very small. The result, when n to infinity, is just lambda 2 over lambda 1 to the distance. I will call it r. R is the distance, b minus a. Therefore, the correlation falls off exponentially. There is a correlation length, c, which is 1 over log of lambda 1 over lambda 2. That's the result. Therefore, the correlation function falls exponentially with the distance. Cannot attain that. If you remember that if there is broken symmetry, it could tend to a constant, which is the square of the magnetization. If it goes to 0, there is no spontaneous symmetry breaking. So it goes to 0 exponentially. And why does it go to 0? Because the eigenvalues lambda 1 and lambda 2 are not equal. The only way of having a large correlation length would be to have a degenerate largest eigenvalue. Okay? Because the eigenvalues are distinct, the correlations fall exponentially with distance. But now we are in position to examine essentially any one-dimensional model. If we take other one-dimensional model, like we saw many, we discussed several models, there will always be, at the end, to diagonalize the transfer matrix. What is a transfer matrix? Transfer matrix, at the end of the day, T is a matrix which have k by k. We have considered up to now k in which k is 2, 3, 4. We have discussed various examples. And it contains here some Boltzmann factor. Term T AB is positive, maybe 0. In fact, never 0. There are always Boltzmann factors. But it could be 0. So matrix T is a matrix with positive entries, real positive entry. Not necessarily symmetric. We have seen non-symmetric matrices. You wrote one this morning. It was not symmetric, the matrix you wrote, but it doesn't matter. T is a matrix of real positive entries. Well, there mathematics helps. There is a theorem which is called the Perron-Frobenius theorem. Which says that for such matrices, the leading eigenvalues, I will explain leading eigenvalue, the leading eigenvalue is 1 over log of lambda 1 over lambda 2 to the n plus a minus b. And here I will get lambda 1 over lambda 1 to the b minus a. I will explain leading eigenvalue. Leading is the eigenvalue with largest modulus, because they could be complex. A priori, there is no reason if the matrix is not complex. So it's the largest absolute value. The leading eigenvalue is real, non-degenerate, and the eigenvector has all terms of same signs. For instance, positive or zero. I will not derive this theorem, it's not very difficult. In fact, it's a theorem that you know in other contexts. When you study the Schrödinger equation, you know that the lowest eigenvalue, it's not the mean, just change sign. The lowest eigenvalue, the ground state, is single, not degenerate, the ground state. And the wave function never vanishes from the ground state. First excited state, there is 1, 0. There is one node in the wave function. Second excited state, 2 nodes, etc. So it's the same theorem, in fact. So it explains what happens in one dimension. The largest eigenvalue, the leading eigenvalue, is real. We found that. Single, non-degenerate, and therefore correlations fall exponential for all one-dimensional model. Correlations fall exponentially with the distance. No long-range order. No long-range order in one dimension. I will give you another example, but maybe we take 5 minutes. I don't want to exhaust you. Stop 5 minutes. I will show you another example of interest. But this proves that in one dimension we cannot have spontaneous symmetry breaking for a discrete symmetry. We will discuss in a short while continuum symmetry. Okay, so I went a bit fast with this calculation. You have to repeat it yourself. Prove that this is true. It's not difficult. I did the calculation in front of your eyes. Maybe you didn't follow the detail, but at the end, you have to be able to prove that, which gives you this. That is not difficult. It's the same technique that we have used up to now. So we stop for 5 minutes, and we'll discuss another problem. Group G2. We could have other discrete symmetry. Yesterday I gave you the definition of the Potts model, which had a permutation symmetry of Q element, slightly larger than Z2. But the mathematics is very similar, at least at the level that we are doing. But we could have more complicated symmetry, like a group J, which is some continuous group, some Lie group. For instance, the rotational group in n dimension. That's a possibility. Here we had an order parameter, which was the expectation value of sigma, which was, we were looking for possibility that this would be non-zero. Here, what would it be? We would have symmetry by rotations, and an order parameter would be some direction of the sphere. So the group J would be broken to a subgroup H if here my parameter varies on the sphere, point on the sphere, it's the expectation value of some vector, I will call it S, So the order parameter would be a vector A vector is an element of the simplest representation R of ON, the trivial representation here that we all know, in which we take vectors. So there is an infinite number of pure states. If I have an external field with a direction, it will orient, it will choose one direction in this sphere. For instance, if my magnetic field H is in the vertical direction, it will choose the north pole here of the sphere. And at zero temperature, we expect that all the spins will align with the north pole. Then there is a residual symmetry group, which is the group of rotation once I've chosen one direction, which is the subgroup ON minus 1. So G is the symmetry of the interaction. H is the residual symmetry when there is spontaneously symmetry breaking. As in this example, some direction is favored spontaneously on the sphere, and G goes to H. H is a subgroup of G, of course. If G is a continuous group depending on P parameter, and H of Q parameters, the number of parameters of what is called the quotient group, G over H, is P minus Q. Let's take the example here. G is ON. What is P for ON? The number of parameters of the rotation group in n dimensions. It's not n. Well, you have to look at an infinitesimal rotation. If I have a rotation belonging to ON, if it's close to identity, it's 1 plus an anti-symmetric matrix, because then R transpose is 1 minus A. A is anti-symmetric, and R times R transpose is 1. So the generator, in fact I should write an exponential, are anti-symmetric real matrices. Well, if you have anti-symmetric real matrices, you have n minus 1 over 2 parameters. Anti-symmetric matrices, 0 and diagonal, you have to choose here n minus 1 plus n minus 2 plus n minus 3, and the other one are opposite. So this is the number of parameters of the ON group. ON minus 1 is, of course, n minus 1, n minus 2 over 2. And P minus Q in that case is just n minus 1. So n minus 1 will be the number of parameters of the phase to describe the phase transition in general. So this is abstract and difficult. Let me take a simple example.
model. Each spin is a vector with n component. And I assume they vary on the sphere. So they are indeed n-1 parameter. This is the same as n-1. I take a lattice, and at each side, I have a vector Si. I will assume that the interaction is nearest neighbor, and I will write the energy of the configuration. A configuration is a choice of vector here, 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 at each lattice side, as minus j, sum of nearest neighbors, Si dot Sj. This Hamiltonian, this energy, is of course invariant by simultaneous rotation of all the spin. If every spin is changed into a rotation times this spin, Si, in which R is the rotation, the same rotation for all spins, this is invariant. So we can ask the same question: is the expectation value of Si, can it be non-zero if we calculate it in the limit in which n tends to infinity and the source, external source, h, going to 0? Or with boundary condition as yesterday. Can that occur? If this occurs, the symmetry would be broken from the rotation group in n dimension to the rotation group in n-1 dimension. A vector order parameter. Be careful that the dimension of the spin, n component, has nothing to do with the dimension of the lattice. The dimension of lattice is 1, 2. This can be completely different. Okay? Again, to show you the powers of transfer matrices, I will solve the one-dimensional 1D solution. So what is Z? Z is the sum of all configuration of exponential minus beta and the energy. Sum of all configuration. What does that mean? That means integral on the sphere S1, Sn, in which this measure ds is on the sphere Sn, minus 1. I normalize to 1. It's the measure on the unit sphere. And I assume that I take as measure of unit sphere 1. If you prefer 4 pi, you can put 4 pi, but I take 1. So this is the definition of Z. So if we are in one dimension, if we are in one dimension, I can write Z equal T S1 S2 T S2 S3 T Sn minus 1 Sn. And again, I will take periodic boundary condition. Integral on S1 up to Sn, in which t, obviously, is exponential beta j S1, S2. The same story, except that instead of a sum on spin, it's an integral on vectors. But it has the same structure of matrix product. In other words, if I take two matrices, A of S1, S2, B of S2, S3, integral ds2, I will call that, by definition, AB of S1, S3. This is my definition of the matrix product. It's a product, it's an integration, it's a matrix, it's a product of kernels rather than a product of matrices, but it's the same. So this Z is equal, again, to the trace of t to the n. Same story with this definition. So we have to find the eigenvalues and the eigenfunction of this kernel T. So the first question is, can we find solution to the following problem. Exponential beta j S1, S2 times some function of S2 integral over S2 on the sphere is equal to lambda times the function of S1. This is the definition of eigenfunction, eigenvalues. Can we solve that? Well, again, we can use the Perron-Frobenius theorem. This kernel is positive, so we expect the largest eigenvalue to be unique, the eigenvector to be positive and non-degenerate. Well, we know one eigenvector, and you will tell me if you can guess one eigenvector. Can you find one function f which satisfies this equation? Well, there is a trivial one. I take a constant. C. Is the integral over S2 a function of S1? The answer is no, because I can make a rotation of S2 and then S1, if I change S2 to RS2, in which R is a rotation, S prime 2, to measure ds2 is invariant, exponential beta j, R minus 1 S1 times S2 times F of S2 is S prime 2. Sorry, RS2. I change S2 to RS2. If I change S2 to RS2, the function is changed to this. This function, I can put the rotation here instead. This is the same. And therefore, if I take a constant, I see that the right-hand side will be the same, will be invariant by rotation. The right-hand side will be the same function for S1 or for any rotation on S1. So if I take a constant here, let me take as constant 1, this integral is of course independent of S1 by rotational invariance. It's rotational invariant. S1 has length unity, so this is just a constant. So we can calculate this constant, some Bessel function. For instance, if we were in 3 dimension, let's take n equals 3, that we all know. I take S1 as the vector 1, 0, 0. This integral is integral 0 to pi, I've normalized by 4 pi, so the sphere is 1. Integral 0 to pi d theta sine theta. Integral d exponential beta j cosine theta. And if I integrate, that's this integral. That's the largest eigenvalue. The integral of the azimuthal angle is 2 pi. So lambda max. Why is it the largest eigenvalue? Because my eigenfunction was positive. All the signs were the same for any value of S2. And Perron-Frobenius theorem tells me that if I find a nodeless function, this has to be the largest eigenvalue. So lambda max is this number, and this number is something like 1/2, 1 over beta j, exponential bits, sich, beta j over beta j. So that's lambda max. Of course, there are many other eigenvalues. They are classified by classical polynomials. They are Bessel's functions, Gegenbach polynomials. It's not interesting, but the next eigenvalue will be this S2 component A. This is A is 1 to n. This is lambda 2. And by rotational invariance, I know this is equal to S1A. This function is the next eigenvalue. This integral, by rotational invariance, integral on S2 is proportional to integral on S1. So is n-fold degenerate, the second eigenvalue. because A can go from 1 to n, and you can calculate lambda 2 very easily by the same trick that we just did. And again, you will find that lambda 2 is smaller than lambda 1 at all temperatures. So this is an example of a continuum symmetry group. And we will see, when we come to more interesting dimension, that there is a big difference between continuum symmetry and discrete symmetry. We will see now, and we will discuss that during the remaining of this morning, that discrete symmetry have spontaneously symmetry breaking in 2 dimensions, but continuous symmetry, no. You have to be in more than 2 dimensions to break continuous symmetries, and there is a lot of physics behind it. It's the physics of Goldstone mode that you may have seen, or maybe you will see with Professor Iopoulos. So we'll stop 10 minutes or 15 minutes, and after that, finally, I will prove you that in 2 dimensions there is spontaneous symmetry breaking with a discrete symmetry.